another draft physics video presentation. Alright, we're going to go over this, collision thing, energy thing. This is really just about energy, and this video was a piece of garbage in terms of conveying understanding of the concept of energy, that energy is a quantity that just isn't that confusing, in the sense that all you really have to understand, if you're sitting in the middle of space somewhere, all you want to know, about the stuff coming at you is how much does it weigh, and how fast is it going, and how big is it. So you just want to know its density, how much, total stuff that is actually moving towards you, how many little bits of matter, and how fast is it going relative to you, because that's all that's going to matter, right? Is the difference in your velocities towards each other. And that's what you're going to want to know, because that's going to mean the difference between whatever, you surviving, not surviving, all of that kind of stuff. And none of this other nonsense, elastic, inelastic, all this crap means anything. So this whole conversation about elastic and inelastic shouldn't even exist, because these are just silly words, because 90% of every interaction, or 99%, have a component of both. They're not perfectly elastic, which means they don't perfectly transmit or transfer energy. It's really hard to perfectly transfer energy. Even the Newton's cradle doesn't perfectly transfer the energy. There's sparks and different little things that happen. So it's not even perfectly elastic. Perfectly elastic would be in some kind of thought experiment, some perfect world. And everything else is some form of less than perfectly elastic. But there is no inelastic. There's no such thing. There's no such category. Anyway. So this video is just so wrong. It implies something that just can't be true. It's impossible for it to be true. That there's any change in the energy of the objects in this thought experiment. And that's what it is. It relates to a real circumstance, and it could have been done with a real circumstance, with a real experiment, and you'd see in the real experiment that none of what she's saying can possibly be true. So anyway, so all I've gotten is garbage comments as a response, and nowhere on the video, not a single person has brought it up as being wrong to do this to energy, to convey some notion that somehow something lost energy when the momentum didn't change, that it's somehow possible not to change the momentum. That is the real momentum. There's no such thing as negative momentum. Let me just, there's no such thing. You can only assign a negative sign based on momentums moving in the same direction, but that doesn't mean there's no momentum, right? If I have two pieces of momentum moving in opposite directions, you wouldn't say, there's no momentum. That would be retarded, especially if the two things are, steel rods that are going to hit you in the head. Okay, there's no way you would say, oh, well, don't worry. The steel rods can't hurt me because, there's zero momentum, because they cancel each other out. No, there's not zero momentum. This is just too stupid. I shouldn't have to make this video. Somebody else should have already made it. Some real physicist should have just pointed out, wow, you're really fucking this subject up. You're confusing issues. There's no confusion here. Alright, so let me play this again and try to make the point. And maybe I'll try to illustrate with like a school of fish, something really simple, what energy is.
Two objects collide and they lock together and move as one.
So that's what she's calling elastic and inelastic. It's something to do with stickiness, which is, in my opinion, just silly. I don't even know why somebody would think this has something to do with stickiness. No, it has to do with whether or not there's some place for the energy to escape. So if the bodies are rigid and they don't allow for sparks to fly off or pieces to fly off, then you'd say they're going to be fairly elastic in terms of their capacity to transfer energy. But there's no stickiness. Stickiness is irrelevant.
The classic example that's going to help us wrap our brains around them is trains. Like those little toy trains with the magnets. Imagine two train cars rolling on a track and then hitting and linking up. It's classic because it's simple. So let's model.
Yes, so how did you screw it up so badly? It's simple, and yet you screwed it up in this amazingly bad way. Okay, where you turn this into Play-Doh somehow. Somehow they lost a whole bunch of energy. No, they didn't lose any energy. You can't have the same momentum and lose energy. It's not possible.
Model it. Give me a good arc. So,
Oh, I forgot it had all this crap in it.
two train cars on a track. We'll say that their masses are M1 and M2.
I gotta speed this up or I'll go insane.
One of them is still, so V2 equals 0. And the other one is moving with a velocity V1. So then they collide and they stick together. Wow.
Yeah, well, they don't really stick together. The sticking together is irrelevant. What is they interact with each other. All right, and the interaction is long enough, there's enough time for there to be a transfer of the energy.
So they collide.
A combining.
And they stick together and they begin moving as one object with a new mass of m1 plus m2 and a final velocity vf for v final. Here's the question that you can solve in a problem like this. Given the initial masses, m1 and m2, and the initial speed, v1, what will the final velocity, vf, be? Like we said, our key idea is conservation of momentum. If we add up the...
Right, so she's not going to add up any, like, how much of the metal was deformed when the couplers banged into each other, how much did they chatter before, you know, the full impact was absorbed. So there were some losses in the system, but she's just basically saying let's just forget about all of the deformation and all of the heat and all of the ways it could have lost some energy. And that's the fact of this thought experiment, okay? She's conceding no losses. That's the only way you could have the same momentum before and the same momentum after. There has to be 0 losses.
Total momentum of the two cars before the collision, that's going to be the total momentum of the coupled cars after the collision. Because one of the cars is at rest to start out with, this problem is pretty simple. Because all the momentum before the collision is in the moving car, M1. Momentum is not...
Right, so again, she just keeps saying it overtly. So we're pretending it's a perfect interaction. Okay, there's no compression of the atmosphere when the two cars come into each other. There's no way for any of the energy to go into space somewhere, or into the environment somewhere, or into the track somewhere. None of the energy can escape. It has to combine into the two objects. It has to be spread.
mass times velocity, so it's m1 times v1. And the momentum of this, p equals 0. And after the collision, that momentum will be in the coupled cars moving together. P final equals the total mass times the final velocity. So m1 plus m2 times v final. So now let's give the cars some masses. Say we give them the same mass, 2 kilograms, and we give the first car a speed of, say, 12 meters per second. Then we work it out to get a total initial momentum of 2 kilograms times 12 meters per second equals 24 kilogram meters per second. And that
Right, so we have 24 kilogram meters per second. So we have a quantity, we have something we can convert into joules if we want to, or into calories, or into any other form of horsepower. We can convert it into any other form of energy. This is how much a spring would be compressed. Okay, so if I have a spring that, you know, with a little scale on it that tells me how much energy something has, you know, I can have that scale, I can measure the energy. That's exactly what this is. This is a measurement of its energy. So let's understand. So we have established it's a certain amount of energy.
that equals our final momentum, which is m1 plus m2, so that's 4 kilograms times v final. And in order to get 24, v final has to be...
Right, so in order to get 24, so it has the same amount of energy. It's just going slower. It's more mass. So it's more fish, okay, moving slower versus fewer fish moving faster. And all you're saying is if there was a tug of war between one car that weighs 2 kilograms moving 12 meters per second and another car weighing 4 kilograms moving half that speed, 6 meters per second, the tug of war would be a draw. That's the fact. Established fact. Makes perfect sense in a perfect circumstance where you're saying there are no losses, nothing was deformed, none of the wheels flew off, nothing unusual happened here. There was just one school of fish absorbed a school of fish that wasn't moving. So a school of fish is going 12 miles an hour, which means it's really just got 12 extra fish that are actually doing all the work. Just means it has 12, it just means it has 12 miles an hour worth of extra fish going this way. And it goes into a school of fish that has a balance. None of them there's no extra fish going this way. So when I combine the two, I still only have the same exact number of extra fish going this way. I don't have any extra fish. I don't have any more fish. And they're just carrying more fish that are not going the right way. So they're dead fish, essentially. So they're just carrying more dead fish. But it's exactly the same number pulling or pushing or whatever you want to call it. It's the same amount of energy.
6 meters per second, so my v final equals 6 meters per second. So 6 meters per second. We ended up with half of the initial velocity, which makes sense because we said the two cars have equal masses, and we only had one of the masses moving at the start. So now you've got double the moving mass at the end. So they must be going half of the original speed if momentum is conserved. And that's
right, if momentum is conserved. If all the momentum stays in the two cars and doesn't go anyplace else, isn't lost to any other mechanism. Now, we know in the real world that would never happen. In the real world, the car would hit going 12, and the second car, when they lock together, would the combined car would probably go something in the 5 range. Okay, there would be some losses. There would be some loss of the momentum because you would lose it as heat and pieces of metal flying off and other kinds of crap. So you would never be able to conserve all of the energy, unless you make a system that's capable. And there really isn't a humanly made system that actually can do that conservation. Perfect conservation.
our basic inelastic collision problem solved using conservation of momentum. But what about
Just absolute bullshit. She didn't solve nothing, blah, blah, blah.
conservation of energy? Is kinetic...
So it doesn't make any sense. Is energy conserved? Of course it is. Momentum is energy. Momentum is the simplest description of something's energy. Again, if you're in space, you're not going to want this equation that says 1/2 mv squared. No, you're not going to want that equation because it's going to lie to you about what's going to happen to you. You want to understand that it's just about mass, and it's just about velocity, and it's just about size. And that's the only thing that's going to make any difference to you, is how dense is the energy coming towards you. I mean, how much space does it fill? And how heavy is it, and how fast is it moving? And that's it. That's all you're going to want to know. That's the energy equation. That tells you everything you need to know. And that's, of course, what nuclear physicists know, because they know that the only thing that matters is how fast is the little electron going, because they know they all have the same mass. And they know that if I have 2 electrons over here going 6 miles an hour, and I have 1 electron over here going 12 miles an hour, that I have exactly the same amount of energy. And it's going to be a draw in the tug of war.
energy conserved in our system here? Surprisingly, no. Let's see why.
Just too stupid. We've already accounted for all the energy. There's no way you can now say, yes, it's the same amount of energy, it's the same amount of momentum. Now we're going to talk about how it's not the same amount of energy and it's not the same amount of momentum. What the fuck? This is too stupid. Nobody cares. It's just too stupid. She's implying to people that somehow you can have the same momentum You did this completely successful, clean transfer of energy, and that somehow you lost energy. Somehow the tug of war is going to be lost. She's going to right now tell you that the thing going, the smaller thing going faster, okay, is going to win the tug of war by a mile. I mean, it's going to just flip the other two cars over and drag them the other way. They're going to lose so badly. That's what she's going to tell you. And it's crap.
By working out the math. Let's calculate the energies before and after the collision. Kinetic energy initial is just going to be 1/2 mv squared. Before the collision, we only...
So again, this equation is horseshit. It's nonsense. I don't know exactly what purpose it's for, right? It was invented doing clay experiments. I don't think it has any relationship to what you're trying to figure out is how much energy can the object impose. And that's all that matters here. If these were asteroids in space, you wouldn't be using this 1/2 mv squared bullshit. It would be totally irrelevant to you. All you'd care about is, you know, how heavy the damn things are and how fast are they moving. And then you start figuring out that, oh yeah, well the heavy thing is going to win here. You know, let's say you had asteroids on either side of the Earth. You know, one's coming at you at 12 and one's coming at you at 6, and it's much bigger. You know, the point is that it's not going to be an equal tug of war, because gravity is actually going to push the heavy thing. It's going to move all of its mass to the same velocity. So you're going to gain that extra momentum. Gravity's going to make more momentum out of the bigger thing than it is out of the smaller thing. And so it is going to be a bigger threat. But that's doing real physics. See, real physics has these subtleties. You got to keep track of this stuff. This mushy nonsense. I have a formula and I'll use it anytime I want to, in any place I want to, even if it's totally inappropriate. That physics doesn't work.
Have the first car moving. So the total energy is 1/2 m1 times v1 squared, which is going to be 1/2 times 2 kilograms.
So she just heard her, right? She said, so the total energy. That's what she just said. So she's saying the kinetic energy is the total energy. There isn't any potential. There isn't any other hidden energy. There's just total energy. And yet she's doing this to it. She's claiming somehow velocity is really, really important and mass is very unimportant. So we're going to square the velocity and we're just going to say, no, we don't do anything to the mass. Mass isn't half the equation. When mass is exactly half the equation. Mass is a block this big and velocity is a block this big. And all you're doing is saying how much space or density the blocks are creating is going to tell you what your total energy is. So if you add mass, you're going to increase your energy. If you add velocity, you're going to increase your energy. And they're both equal in terms of their capacity to contribute to what is going to be your energy, your momentum.
Times 12 meters per second squared, which works out to 144 joules. After the collision, so our final kinetic energy equals...
So final kinetic energy, so she said it differently, but it's the same thing, right? Because there is no hidden energy anywhere. The only energy in the equation is your motional energy, okay? How you're moving on the track. There is no any other form of energy. There's no going up hills, there's no going down hills, there's no anything else that's creating any energy in the experiment. All right, so the only thing we can talk about is your kinetic energy, and that is your total energy, and it has to equal your momentum. It has to. There's no other way you can do it. It's no other logical thing for you to understand. You can't say the two things have the same momentum, yet they have different energies. It's not possible to do that. It's retarded. It's overtly nonsensical rubbish.
1/2 mv squared. But my final mass is both masses together, which equals 4 kilograms. So this equals 1/2 times 4 kilograms. And then my final velocity squared, so my 6 meters per second squared. And that equals 72 joules. So we lost kinetic energy.
So again, she's saying somehow there's a loss of kinetic energy. She's saying the car moving 12, the half is heavy car moving 12 whatever meters per second will win the tug of war. It has twice as much energy to win the tug of war with. So it will flip the other two cars over and drag them in the other direction. Now we know that's not going to happen. We know that, nope, it's exactly the same amount of energy. There's just as the same amount of energy moving in the two directions, or in the same direction, however you want to look at it. It's the same amount of energy. You can't sit there and say one of them has more energy. It's just nonsense.
So what happened to the energy? Well,
so again, so she just said it. What happened to the energy? Now, you know they have the same momentum, so they didn't lose any energy. You know, logically, you know that if there was a tug of war, it would be a draw. So there is no imbalance in the energy, so it didn't go anywhere. It couldn't have gone somewhere. It didn't go anywhere. It's still in the moving cars. That's the total amount of energy is still in the cars. And so now she's going to talk about how, well, it went to all kinds of deformation. And it flew over there, and it went over there, and it went over there. If it did all those things, then the momentum would be different. You can't have the same momentum. Again, you can't conserve the momentum and lose energy. You can't do that. It's not possible. And I'm talking about the real momentum. Again, there's no such thing as a positive or negative momentum, okay? There's just no such thing. That's just nonsense. So this isn't about which way the vector is pointing. It's about how long the vector is. That's your momentum, is a vector pointing in a direction. And it's just about how much you have we're talking about here. We're not talking about cancellations and all that nonsense, because guess what? They don't exist in reality. Okay, the vector has to be satisfied. Okay, you can't destroy the energy. You can just make pieces of it fly off in directions. All right, and again, the experiment was explicitly stated. There is no pieces flying off in directions. There is no loss of the vectors of momentum. The vector of momentum completely went from one car into two cars. The same vector is still in the two cars. So there can't be any losses anywhere, or the vector would be shorter. I mean, this is so dumb.
Inelastic collision, when the colliding objects stick, some of the original kinetic energy is lost.
Okay, so there was no losses of momentum, but we lost energy. It just can't be the truth. It's a stinking lousy mistake. It's garbage. I mean, I should call it something more dramatically bad, because this is actually in teaching videos. They actually teach this shit. That somehow you lost energy even though you have the same momentum. They apparently believe this is possible. Some of them. And apparently the physicists who know better just don't have the guts to say, gosh, that's insane. You shouldn't be telling people that garbage. Why don't you just why don't you start claiming that, you know, particles aren't particles and they actually have a frequency and they superimpose and fly through two slits? Why don't you tell them all that kind of crap? If you're going to tell them crap, why don't you talk about them being entangled or something? It's so silly. Why don't you do that too? I mean, this is just so fucking bad. Dark matter. Why don't you tell them there's stuff called dark matter that's like an invisible man? Yeah, it can just do sneaky things, but you can't tell he's there. Why don't you tell them that one? That's a funny story too.
Some of it escapes as heat. Oftentimes it goes into the object's mechanical deformation.
Oh yeah, it's just like two trains hitting each other. The old egg hitting the apple thing. Just like two trains. Apples is made of steel, ain't they? Huh? There? So she said this is what happened when the two trains collided. That a whole bunch of energy flew off, and half the energy. One half of the energy flew off, and we just didn't notice. But it retained all of the momentum. The apple flew off at exactly the same speed as the egg. I mean, exactly half the speed with twice the mass. Yeah. So we lost half the energy, but we didn't lose any of the energy. Isn't that cool? You can lose half of it, but not lose any of it. That's like perpetual energy, isn't it? So Tesla would love this. This is Tesla theory all over the place. Free fucking energy. All you have to do is make things go fast enough, and you don't need any. You can have perpetual, eternal, forever energy because you get to square the velocity and just keep growing your amount of energy. So keep reducing the mass. So all you have to do is take something that's going fast and cut its mass off, and you get free energy. Yeah. Shit.
You throw an egg against the wall and it deforms, or a ping pong ball hits some fruit and it deforms. The energy isn't...
Oh, it's a ping pong ball. Oh. God, this is so annoying. So again, she just now recited a whole bunch of losses of energy. Deformation, pieces flying off. None of those were in the experiment. She didn't show us how the momentum did that. The momentum flew off in little pieces somewhere. Nowhere did the momentum fly off in little pieces somewhere. It was completely conserved in the trains. But yet, somehow, half the energy is gone. It's amazing. Yeah, I'm just saying, how it's just terrible. It's terrible. I mean, people are so dumb. It's amazing that 17,000 people have watched this video and not one of them can say, how the fuck can you say something so stupid?
lost to the universe, but it is no longer in...
So nothing was lost to the universe. Again, her whole experiment, nothing was lost to the universe. The momentum is exactly intact. How could anything be lost to the universe? How could you have this? I keep saying the same thing. How can you preserve all of the momentum and yet lost half of the momentum?
a system of the two things that collided, so we can't easily measure it. So when you have a collision where things...
So again, now she's claiming, well, it all happened invisibly and I didn't see it. It escaped. It all was sneaky. But how could the momentum still be there then? How is it going 6 miles an hour? It can't go 6 miles an hour if it lost energy. If you have twice the mass and you have half the velocity, then you have the total amount of energy. So it had to go slower then. Duh.
Together afterwards, you can't use conservation of energy to solve those problems. And that's where the word inelastic comes from.
No, it doesn't. So that's just bullshit. Don't blame anybody in the past for being as stupid as what you're talking, the shit you're talking. None of them thought, okay, you could have the same momentum and have half as much energy. None of them thought that.
The objects that collide deform, and they don't elastically return to their original state.
Right, well that didn't happen. Where in your little experiment did the train turn into a different shape? It never looked like a little elephant or a guinea pig. None of that ever happened. So that's all crap that you've made up now, okay? And it still wouldn't make any sense because then you couldn't explain how the momentum vector broke into pieces and went in all kinds of directions, okay? And yet somehow the momentum vector is all intact. Except it's lost half of its length because it's lost half of its energy somehow. Somehow it's only going to compress the spring this much.
So, done with inelastic.
Alright, so anyway, I didn't even play the rest of this video. There's probably all kinds of crap in here that you just say, what the fuck is she talking about? And how does she get away with it? And how is this, it's just such bad physics. Alright, so I'll attempt to metaphor this in some way that makes it more understandable, or how I relate to it. Okay, let's just say this is how I relate to it. So we know that the energy is really inside of everything. We're really not talking about how much, if I broke all of your atoms, how much energy you have, right? We're really just talking about energy as a comparison between two big systems, two universes, and how much of their stuff it has a prejudice in a direction. So I could argue that you kind of understand your mass as being a bunch of fish. Let's just say you're just made out of fish, all right? And the idea is that your velocity is going to be when you add up all your fish and their directions, do you have extra fish going in more in one direction than another? Where's there an imbalance? So if you had an imbalance where you have one little extra fish going this way, right, and you have another extra fish going this way, you could sort of understand that your balance would be a fish going this way. Okay, that I could take those two fish, combine them, and I could create and say you have one extra fish going in this direction. All right, and that's going to create your velocity, and it means that this one extra fish, okay, he might be going, let's say, 100 miles an hour in free ocean, but the truth is he has to drag all of these fish with him. So dragging, if I take him and divide his velocity into all the other fish, say there is 100 fish in here, well, then his velocity is turned into 1, okay, 1 meter a second or whatever, right? Because I have to divide it by all the fish. So then if I crash him into another school of fish that has, I could have a vector in a direction, an extra, but let's just say this system doesn't have an extra fish going in one direction. So it has exactly 50% of the fish are going that way, and 50% going that way, and 50% this way, 50% that. They all completely balance each other's movement. And now I'm going to combine the two. I'm going to turn it into one big school. All right. It's still only got this one fish. That's all it's got. It's him. And so now, okay, its velocity is going to be spread over 200 fish. Because now it's got to drag all of these fish with it, with its extra. Okay, it's a little extra tugging power. And so now it's only going to be going a half of a meter per second. Because it's got twice as much crap to carry with it. Okay? But the point is if I was going to have a contest, if I was going to sit there and have a contest between the before fish, the before school, and then the after school, all right? So the big school versus the small school with the 1 meter per second, and the big school that's only going a half meter per second. The fact is, if I had a tug of war between, say this one's the new version, it's going 1/2, but it's bigger. So obviously, because I drew this second circle, I'm confused my own drawing, but whatever, you can get the point. The point is the tug of war would be a draw. Okay, the original condition and the new condition is really, all you're really saying is what's the extra fish? This only has one extra fish, that one only is going to have one extra fish, so the two of them have the same exact amount of energy, the extra fish, the fish going in the other direction, and that's all you ever have. So all you're really doing is counting the fish that are out of balance. That's it. There's nothing else to count. That's the momentum, that's the energy. The energy is whatever isn't undone by something going in the opposite direction. So whatever doesn't have, whatever isn't yin-yanging, okay, you either have a little bit of extra yang or a little bit of extra yin, all right, and that's your energy. And that's all your energy. There isn't any other place to get it from. You have to have that. So again, it just, there's no way you turn this into anything other. You can't kill the energy. So when she did the experiment, the one car, okay, crashes into the second car, and all it did was absorb the extra dead fish, okay, reducing the velocity, but continuing with the same, now the number of fish has increased, so the amount of mass, the amount of stuff you're hitting with, okay, at that speed. But the original fish was going 100 miles an hour, 100 meters per second, the original fish by itself. And so all you're saying is yes, it's still the original fish power. You can't change the fish power. You can't change, if you have with horses, the extra horsepower. So you only have, you have a certain horsepower in here. You combine it in here by adding extra weight to the horse's wagon. You haven't changed the horsepower. You'll change how fast the horse can move, but you haven't changed how much power the horse has. So you can't have less energy. It's not possible. I don't know if that helped or not, but this really shouldn't be an argument with rational people. It really shouldn't be an argument. I mean, it's overt what she did. It's overt. She said there's no loss in momentum because there's no losses to the environment. There was no losses to the coupler. There was no losses anywhere. And then she says, oh, but no, there was half the energy was lost to a bunch of causes. You can't say that. You can't do that. You can't say the energy is in any way changed. The same amount of energy is possessed by the trains. If I do the actual tug of war, I'm going to be correct, and it's going to be a draw. Okay? The train that's lighter going 12 miles an hour will not flip the other two trains over and drag them in the other direction. None of that will happen. They can't have different amounts of energy and have the same momentum. They can't do it. So, I don't know what else to say. I mean, the world is just too silly. I mean, the idiocracy is just so on the march. You people just are, you really are just belligerently stupid. This is junk. It's garbage physics. Whether you want to argue that she's using the wrong vocabulary, or she's calling it the wrong thing, blah blah blah, some other kind of crap, that's fine with me. But you have to just concede that there's no way, if you you look at what she's saying, it can make any sense at all. You can't have a conservation of momentum and a destruction of energy. You can't do that. It's impossible. No, it really should be enough. But what, I really have to keep going on this subject? I mean, that's what's going to take place here, is your people are just going to belligerently argue that, no, what she said is perfectly rational and sensible. It makes perfect sense. It's just the way you want to teach a kid about what this fucking stuff is going on here, that somehow you fundamentally change the energy by just adding some more, by throwing more coal in the train. You somehow fundamentally changed how much energy the train has, when you didn't. The engine's still the same engine. It's still, the wheels are the same wheels. The whole thing is the same system. You can't change its energy by adding cars. You can't change the energy of the train by adding cars. It's that simple. It doesn't matter how many cars I add. I can't change what the engine is doing. That's what you should be teaching. Fuck. Alright. So, I don't know what to say. This is just too. I didn't think things would get this silly. Where you can't even point out how this is just rotten physics. It just doesn't have anything to do with real physics, and you people are still going to defend it. I mean, it just stuns me that you have so little integrity. Stunning. I mean, it surprises me. I just didn't think smart people were this such lying scum. Really just didn't think so. But apparently they are. That's all there are. That's all there is on this planet. Just lying scum. Horrible, terrible.